In this video, we're going to talk about volume and surface area in higher dimensions, and this will be part 1 of 2. And when I say volume and surface area, what I'm talking about is volume and surface area of a ball in different dimensional spaces. So, for example, if we're in three-dimensional space and we look at a sphere, okay, so we have an x-axis, a y-axis, and a z-axis here. And so we think of a point, and the set of all points whose distance to that center point is less than r. Okay, that would be the ball. Now, the boundary of the ball is what's called the sphere, but the ball is the interior to the sphere here. And we have these familiar formulas from geometry. The volume of a sphere is 4/3 pi r cubed. Okay, the volume of that ball. Okay, the surface area is 4 pi r squared. Okay, now where do these formulas come from? Well, there's different ways that you can derive these formulas. Now, when we're in two-dimensional space, a ball doesn't really look like a ball. It really looks just like a circle, or the interior part of a circle. So when we think of a ball, it's the set of all points whose distance to some center point is less than r. So all these points in here would be inside that ball. Now, when we want to measure how big the inside of this ball is, the inside of this circle is, well, we use area, right? And the area is pi r squared. Okay, but I want to still call the interior part of this volume. Even though it's really area, I'm going to call it volume. So we're thinking of the volume as how big the interior is. And so in this case, it's really an area, but we'll think of it as a volume. It's pi r squared. Now, the circumference of a circle, okay, is 2 pi r, but we're going to kind of think of that as a surface area, right? It's like a measure of the boundary, okay? Even though it's really a length, right? It's a circumference, 2 pi r. We're going to think of that as like a surface area. So we talk about a ball in different dimensional space. We'll think of the volume as like a measure of how big the interior of the ball is, and the surface area will be a measure of how big the boundary of that ball is. Now, here is a really interesting table that gives us the volume and surface area of a ball in different dimensional spaces. So, for example, if we're in Rn where n is 3, so we're in three-dimensional space, the volume of a ball is, again, 4/3 pi r cubed, and the surface area is 4 pi r squared. Okay, if we are in two-dimensional space where we really have a circle, the volume is pi r squared, and again, that's really area. And the surface area, which is really circumference, is 2 pi r. But what's really interesting is we have these different formulas, though, even for a ball in four-dimensional space. Okay, we can find the volume and the surface area of that ball. Okay, in all these different dimensional spaces, I go all the way up to dimension 10, I find formulas. Now, it's really interesting where these formulas come from, and we'll point out a few things. But let me mention a couple things. So I already mentioned that in dimension 2, this is really area, this is really a length. In dimension 1, what do we mean by a ball of radius r in dimension 1? Well, a ball of radius r, let's say centered at 0, the point 0 on a number line, would just be the interval from minus r to r. Okay, the interval from minus r to r. And notice the volume would be really the length of that interval, and that's 2r. And the boundary, how big the boundary is, well, the boundary is really just two endpoints, the point at minus r and positive r. So the surface area would just be like the number of endpoints, which is just 2. Okay, now a couple of things are really interesting. Notice that the volume for these formulas, in dimension 1 it has a r, in dimension 2 it has a r squared, dimension 3 we have r cubed, r to the 4th, r to the 5th, and it keeps going up like that. We also have a pi here, and then a pi here, then a pi squared, and a pi squared. Okay, and then a pi cubed, and a pi cubed, pi to the 4th, pi to the 4th, and so on. And then we also have these strange coefficients here. Okay, for the volume of a ball of radius r in different dimensional spaces. And we have similar types of things happening for the surface area. Now notice, instead of having an r squared here, we just have an r to the 1. Instead of having r cubed here, we have an r squared. The power on r is always 1 lower than the power for the volume. Okay, and we also have some of these kind of strange coefficients. Okay, where are these coming from? Okay, so I want to really study this table and look at this table and ask ourselves a few questions about this table. So let's go down to a couple questions. This is what I already mentioned about how this, when we talk about volume in dimension 2, we're really talking about area, and surface area really means circumference. Okay, but a couple questions here we have is, first of all, where do these formulas come from? Okay, where does that table of formulas even come from? A second question we can ask is, why is the volume of the unit ball largest in dimension 5? Now, what do we mean by that? What do we mean by unit ball? Well, a unit ball is a ball of radius 1. So notice if we just plug in 1 in each of these formulas for the volume of a ball of radius r, so we let r be 1. Well, for example, the volume of a ball of radius 1 when we're in three-dimensional space, when it actually looks like a ball, well, it'll be 4/3 pi times 1 cubed. So in other words, it's really just 4/3 pi. Now, 4/3 pi is really about 4.19. Okay, or the volume of a ball of radius 1 when we're in two-dimensional space. So really we're talking about the area of a circle of radius 1. Well, it'll be pi times 1 squared, which is just pi. Now notice the volume looks like it's getting bigger. Okay, volume of a ball of radius 1 is 2 here, then 3.14, then 4.19, 4.93, 5.26. But then notice it drops down to 5.16. 4.72, 4.06, and then it keeps getting smaller and smaller. So why is it the case that in dimension 5, the volume of the unit ball sort of maxes out like this? Okay, what's so special about dimension 5? Okay, other questions here. So notice that the derivative with respect to r of the formula for the volume of a ball of radius r gives the formula for the surface area of the ball. So why is that true? So what do we mean by this? Well, notice, what's the derivative of pi r squared? If we're taking the derivative with respect to r, well, wouldn't it be 2 pi r? Okay, what's the derivative of 4/3 pi r cubed? Well, if we take the 3 out front and lower this to 2, notice 3 times 4/3, that'd be 4, and we would get 4 pi r squared. That's the surface area. It actually works in every dimension, even in dimension 1, right? The derivative of 2r is just 2. Okay, derivative with respect to r. So why is that the case? Okay, it's a really interesting observation, but why is that the case? So these are really the questions that we want to answer. So where do these formulas come from? Why is the volume largest in dimension 5? And why is the fact that the derivative of the volume formula here gives you the surface area formula if you're in a particular dimension? Okay, so we're going to answer those questions in these next 2 videos. Okay, so a couple pieces of notation. Well, let's let V sub n of r denote the volume of a ball of radius r in Rn, and S sub n will denote its surface area. Okay, so if we're in n-dimensional space, okay, then the V sub n of r will denote the volume of the ball. So for example, V sub 3 of r, if we're in 3-dimensional space, the volume is 4/3 pi r cubed. Okay, and S sub 3 of r, if we're in 3-dimensional space, that ball, it'd be 4 pi r squared. Okay, so we're just going to label this V sub 3 of r, this formula, and this would be S sub 3 of r. Okay, now in order to figure out where these formulas come from, we have to do a computation. Okay, so we're first going to find the value of this integral. Okay, the integral from minus infinity to infinity of e to the minus x squared dx. Okay, now how can we evaluate this integral? Now, notice things would be a lot easier if we could do like a u substitution. For example, if we could let u be negative x squared, then du would be negative 2x dx. But notice we don't have a negative 2x dx. We don't have that x dx that we need. Okay, so how do we find this, the value of this integral? Now let's actually look at this function e to the negative x squared. What does the graph of that look like? Right, we're talking about a definite integral, an improper integral here from negative infinity to infinity. What does that graph look like? Okay, now I've brought up here the Desmos website. This is a great website. It has an online graphing calculator. Let's type in y equals e to the negative x squared. And notice what the graph looks like. Okay, it's like a bell curve. Okay, and the question really is, what's the integral of this function from minus infinity to infinity? What's the area underneath this curve, right? How many square units do we have? Okay, now notice it looks like it's going to be probably more than 1 square unit because, okay, 1 square unit would be this amount. But notice if you look at just even from minus 1 to 1, this kind of looks like it's at least 1 square unit, and you have a little more over here and here. A question you could ask is, do we get a finite answer for the in other words, does this integral converge or does it diverge? Well, I think this is going to go down to the x-axis fast enough that we're actually going to get a finite area here. Okay, so the question is, what is that area? How do we find it? Okay, so first of all, to find the value of this integral from negative infinity to infinity of e to the negative x squared dx, we're going to find the value of this integral. Okay, we're going to look at this double integral. Now notice this is not the same integral here. This is the integral from minus infinity to infinity of the integral from minus infinity to infinity of e to the minus x squared plus y squared dx dy. So this is actually a surface, and we're going to find really what's the volume underneath this surface. Okay, in fact, if we come back here to Desmos, we can type in e to the negative, and let's put x squared plus y squared in parentheses here. And notice what we have here is a surface that lies above the xy plane. This is the xy plane down here. We can kind of rotate this around a little bit. In fact, you can see here, it's sort of like a bell type shape, only it's a three-dimensional shape. I mean, the surface is two-dimensional, but you're trying to find the volume underneath that. And so instead of finding an area under a curve, you're trying to find the volume underneath here from that's above this xy plane. Okay, so that's what this integral is really trying to do. The integral of this function, okay, of two variables. Okay, so it's kind of crazy, but we're going to calculate this integral. It's sometimes called an auxiliary integral, and that's going to somehow help us find the value of this integral, which is really what we're interested in finding. Okay, so one way of finding the value of this integral is to break things apart. We can write e to the negative x squared plus y squared as e to the negative x squared times e to the negative y squared. Right? It's just property of exponents there. You can break those apart. But then notice this inside integral is really an integral with respect to x, and we have this e to the minus y squared. So that's constant with respect to the x there. Right? So we can pull this e to the minus y squared out in front of the integral, and that's what I've done in this step here. Now this integral is actually just going to be a number. As long as this integral converges, this integral will just be some number, and we can take this number and pull it outside of this integral with respect to y. So we brought it out front. So notice we really have a product of two integrals. Integral from negative infinity to infinity of e to the negative x squared dx times the integral from negative infinity to infinity of e to the negative y squared dy. Now I got to ask you, which of these integrals do you think is going to be bigger? Which is going to give you the bigger value? Well, it turns out they're going to give you the same value, right? Because they're really the same integral. You're just using a different, well, what's called a dummy variable. So the integral from negative infinity to infinity of e to the negative x squared dx would be the same thing as if we were doing the integral of e to the negative t squared dt, or e to the negative m squared dm, right? The letter that you're using doesn't matter. It's not going to affect the value of the integral. So notice these are really the same integral here. Okay, so what we really have is this integral squared. And notice, by the way, this integral is really the integral that we're trying to find. So one way of calculating this double integral gives us this as our final answer. And we're kind of stuck here. We can't really go any further. We're just stuck here. But actually, another way of calculating this double integral is to use polar coordinates. Okay, and if we change to polar coordinates, notice x squared plus y squared becomes r squared. Right? When using polar coordinates, r squared is x squared plus y squared. And remember that the dx dy turns into r dr d theta. Now this is really good because now we can do a u substitution. And if we let u be r squared or negative r squared, the du is going to be a 2r dr, negative 2r dr, and we have the r dr that we need now. So this works out really well in polar coordinates. Now we have to change our limits of integration. We're really integrating over the whole xy plane, right? X goes from negative infinity to infinity, and so does y. And now if we change it to r and theta, we just have to let r, the radius, go from 0 to infinity, and theta go from 0 to 2 pi. That will take care of the whole plane, right? Okay, so if we actually do this, so if we do this u substitution with u equals to negative r squared, then du would be negative 2r dr. And then we have, we can plug things in here, and notice this is the integral that we get. We end up having e to the u, right, because negative r squared was u. And then the r dr ends up being negative 1/2 du. And we can take the negative 1/2 out in front of this, and what's the integral from 0 to negative infinity of e to the u du? Well, the integral of e to the u du is just e to the u, evaluated from 0 to negative infinity. If you plug in the negative infinity, you get 0, right? E to the negative infinity is like 0. And then e to the 0 is 1, so you get 0 minus 1. And if you work this out, you end up getting pi as your answer. So this would really just be positive 1/2 here. The integral of 1/2 with respect to theta is going to be 1/2 theta. And if you plug in the 2 pi and the 0 and subtract, you're going to get 1/2 times 2 pi minus 1/2 times 0. So it ends up just being pi. So what's really interesting is we calculated this double integral two ways. One way, we got the actual answer to be pi. Okay, that was that total volume underneath that surface was pi. Another way of calculating, though, we got that it was equal to this. So actually, shouldn't this equal pi? Okay, because both of these things equal the value of this double integral. Okay, so notice we can equate our answers and we can say that this thing squared is equal to pi. So again, what did we do? Well, we calculated this integral two different ways. One way we calculated, we got this as our answer. The other way we calculated, we got pi as our answer. So this thing should equal pi. Right? So notice that's what I have. This thing equals pi. So notice this integral squared equals pi. So this integral will be the square root of pi. Now we don't have to worry about it being negative the square root of pi because this integral can't be negative. We're integrating a positive function here from negative infinity to infinity. So this integral that we were looking for is the square root of pi. Right? That's a really fascinating way of trying to find this integral. We actually did a double integral to help us find the value of this integral. Okay, now notice also by symmetry, because e to the negative x squared, remember, is that bell curve. It's symmetric with respect to the y-axis. In fact, let's bring it up again here. If we wanted to find the total area underneath this curve, shouldn't it be just double the area from 0 to infinity? So if we just take this region from 0 to infinity and double it, then we would get the total area. Okay, so if this integral from negative infinity to infinity of this was the square root of pi, the integral from 0 to infinity should be the square root of pi all over 2. Right? So integral from 0 to infinity is just 1/2 the square root of pi. Okay, so we're actually going to use this value, okay, and also this right here later on, as you'll see. But let's continue on. Now, we're going to learn about something called the gamma function, and you may actually have heard of this before. This is a really interesting function. It's a famous and important function as well. So what is the gamma function? Well, it turns out it's an interesting way of extending the factorial function to non-integers. So consider the function f of n equals n factorial. Now I'm using the letter n because typically we use n when we're thinking about whole numbers, okay, rather than things like decimals and fractions. So for example, for this function, f of 5 would be 5 factorial. Now 5 factorial means 5 times 4 times 3 times 2 times 1, and I think that's 120, right? So f of 5 would be 120. But notice we can only plug in these nice whole numbers here, non-negative whole numbers for n. For example, f of 4.7 wouldn't make sense. What's 4.7 factorial, right? That doesn't even make sense. But what if we'd like to have an idea of what is 4.7 factorial? Well, that's where the gamma function kind of comes into play. Okay, so we'd like to find a function that extends the factorial function to all real numbers. Okay, and so this is possible with the gamma function, okay, or almost all real numbers. Okay, we define the gamma function as follows. Okay, this is going to look like a weird definition, but gamma of n is equal to the integral from 0 to infinity of x to the n minus 1 times e to the minus x dx. Okay, now I've used, in this definition, I allow n, though, to be any real number. So even though I'm using n, I'm thinking of n as being, let's just let it be 7.3 or 4.7 or something. Let's let n be a real number, not necessarily just a whole number. Okay, now what is this? Okay, well, we're really trying to find the area underneath a certain curve here. So for example, gamma of 5 would be the integral from 0 to infinity of x to the 4th power, right? 5 minus 1 x to the 4th times e to the minus x dx. Okay, now it turns out though that if n is a nice whole number, it's going to turn out that gamma of n is n minus 1 factorial. So for example, gamma of 5, it's going to turn out it's 4 factorial, or in other words 24. Gamma of 6 would be 5 factorial, so it'd be 120. Okay, but why is that? I'm just telling you that. I want to actually show you this though. Okay, so it's kind of a strange definition, but let's use this definition to first of all compute what's gamma of 1. Now go back and look at our definition. Gamma of n is this. So gamma of 1, if we plug in 1 for n, this would be x to the 0 power, and that's really just 1. So it's really the integral from 0 to infinity of e to the minus x dx. That's what gamma of 1 would be, right? Okay, we plug it in, x to the 0 power is just 1. We plug this in, well, the integral of e to the minus x is negative e to the negative x, and if you plug in infinity, you're going to get 0, and you plug in 0, you're going to get negative 1, so you end up having 0 minus a negative 1, ends up giving you 1. Okay, so gamma of 1 is 1. Now, what about gamma of n plus 1? We're going to use integration by parts to simplify gamma of n plus 1. Now remember, our formula for gamma is this, gamma of n. So what would gamma of n plus 1 be? Well, if we replace this n with n plus 1, then we'd have to replace this with n with n plus 1. So it'd be n plus 1 minus 1, that would just be n. So gamma of n plus 1 is going to be the integral from 0 to infinity of x to the n times e to the minus x dx. Okay, so that's what gamma of n plus 1 is, and that's what I've written here. So notice, integral from 0 to infinity of x to the, it's really n plus 1 minus 1, but that's just n, times e to the minus x dx. Okay, now it turns out if you do integration by parts here, so if we let u be x to the n, and the dv be the e to the minus x dx, then you can figure out what the du would be. The du would be n times x to the n minus 1. And you can figure out what the v would be. The v would be negative e to the negative x. Okay, and if you work this out, this is what you get. So use integration by parts right here. So you can try this on your own by hand if you want to. But notice what happens. Well, notice here we have a negative negative, that becomes a plus, and this n can come out front. And what we have here, it turns out that if you plug in 0, you're going to get 0. Okay, if you plug in infinity, you're really also going to get infinity, although it's not quite so clear. It's almost like you have infinity to the n over e to the infinity with a negative out front. But if you use L'Hopital's rule, like n number of times, I guess you can see that that would really be 0. So the point is that if you plug in infinity, or if you plug in some variable and let that variable approach infinity, okay, take the limit as it approaches infinity, you might have to use L'Hopital's rule, n times, but you'll get 0 minus 0. So the point is that you get 0 minus 0, which is 0, okay, when you do that integration by parts, plus this thing here. But notice this is n times this integral. This integral is just gamma of n. Okay, that was the original formula for gamma of n. So it turns out that gamma of n plus 1 is n times gamma of n. Okay, so again, I challenge you to think this through. I did it kind of quickly here, but gamma of n plus 1, figure out what that is, and then use integration by parts and work things out. It should end up equaling n times gamma of n. Okay, so this gives the following fact, which is true for all real numbers n, okay, not equal to 0, not just whole numbers. The gamma of n plus 1 is n times gamma of n. Okay, gamma of n plus 1 is n times gamma of n. But notice we already found gamma of 1 was 1, right? We did that calculation. So what's gamma of 5, let's say? Well, notice gamma of 5, if you let n be 4 in this formula would say that gamma of 5 is equal to 4 times gamma of 4, right? If you just let n be 4. But notice what's gamma of 4? Well, if you try to find gamma of 4, notice you let n be 3, this will say gamma of 4. So if we let n be 3 everywhere here, gamma of 4 would be 3 times gamma of 3. Okay, so notice that gamma of 5, which was 4 times gamma of 4, well, gamma of 4 is 3 times gamma of 3. It's going to turn out gamma of 3 is 2 times gamma of 2, and gamma of 2 is going to be 2 times gamma of 1. But gamma of 1 was 1. Okay, I put an extra 1 there accidentally. But notice what we end up with is 4 times 3 times 2 times 1, and that's 4 factorial. Okay, so gamma of 5 ends up being 4 factorial. Turns out that gamma of 6 would be 5 factorial, gamma of 7 would be 6 factorial, and so on. So it's an easy induction argument. You could actually prove it using induction to show that for any positive integer n, gamma of n is n minus 1 factorial. Okay. Now it turns out though, the key thing about gamma though, so if n is a positive whole number, so gamma of 7 would be 6 factorial, that's true, but it also turns out that we can find gamma of n even if n is not a nice whole number. Okay, so for example, let's let n be 1/2. Okay, what is gamma of 1/2? Okay, this is going to be really interesting. If we go back to our original definition of gamma, what's gamma of 1/2? Well, if n is 1/2, plug in 1/2 here. Well, 1/2 minus 1, that would be negative 1/2. So gamma of 1/2 is going to be the integral from 0 to infinity of x to the negative 1/2 times e to the minus x dx. Okay, so let's go down and find it here. Gamma of 1/2 is integral from 0 to infinity of x to the minus 1/2. And again, where that comes from is taking 1/2 and subtracting 1. 1/2 minus 1 is negative 1/2. Okay, times e to the negative x dx. Okay, now it turns out you can do a u substitution with u equals x to the positive 1/2. So it's kind of crazy to work this out, but I challenge you to do this. If u is x to the 1/2, You might think, why am I doing x to the positive 1/2? Because there's an x to the negative 1/2 here. Well, the du would be 1/2 x to the minus 1/2. And then you can kind of actually go back and resolve this for x. X would be u squared. And so it turns out that e to the minus x is like e to the minus u squared. And this x to the minus 1/2 dx is really just the du. Okay, so it's kind of a strange u substitution I did there. But if you let u be x to the positive 1/2, du would be 1/2 x to the minus 1/2. And that 1/2 x to the minus 1/2 is what we have, dx is what we have here, x to the minus 1/2 dx. Now you have the 2 up front because of the 1/2 coefficient. But then notice also, what about e to the minus x? What does that become? Well, x is u squared. Right? If you square both sides, so e to the minus x would be e to the minus u squared. But now notice this integral from 0 to infinity of e to the minus u squared du, that's the integral that we did before, right? That was the one that's the square root of pi all over 2. Right now I'm using u here instead of x or instead of t or whatever, but that's what it is. Oh, by the way, you can change your limits of integration, right? So we go from 0 to infinity. It stays 0 to infinity though, right? If x is 0, u is 0. And if x is infinity, u is infinity. Okay, so notice we get 2 times the square root of pi over 2. We get the square root of pi. Right, so we really needed the value of this integral to calculate gamma of 1/2, and that's why we calculated it before. So gamma of 1/2 is the square root of pi. Okay, so this fact, along with this fact, now gamma of n plus 1 equals n times gamma of n, that was true regardless of whether n was a whole number or not. Okay, so let's use the fact that gamma of 1/2 is the square root of pi, along with this to find gamma of different values. So let's say if n is 1/2, what does this formula say? Well, this would say gamma of 3/2, right? Gamma of 1/2 plus 1 would be gamma of 3/2 equals 1/2 times gamma of 1/2. So gamma of 3/2 is 1/2 times gamma of 1/2. But we already found gamma of 1/2 was the square root of pi, so it's 1/2 the square root of pi. So gamma of 3/2 is the square root of pi. Now gamma of 5/2 ends up being 3/2 times gamma of 3/2, right? If you let n be 3/2 in this formula, this would say gamma of 5/2 equals 3/2 times gamma of 3/2. But what's gamma of 3/2? Well, we just found that. Gamma of 3/2 was 1/2 the square root of pi. So we have 3/4 times 1/2 the square root of pi, we get this. Gamma of 7/2 is 5/2 times gamma of 5/2, but what is gamma of 5/2? We just found this. So notice we get these formulas for gamma of 1/2. So what's really interesting is we know gamma of 1 and gamma of 2 and gamma of 3 and gamma of 4, because those are just the factorials, right? Gamma of 4 is really 3 factorial, which is 6. Gamma of 5 is 4 factorial, right? Which would be, what, 24, right? Gamma of 6 would be 5 factorial, which is 120. But we also have gamma of 0.5 and 1.5 and 2.5 and 3.5 and 4.5. We get these interesting values. By the way, these coefficients here may look familiar to you. So you see like a 15/8, a 105 over 16, 945 over 32. If you go back to our original table here, you might start seeing some of these numbers, right? So 16 over 105, 32 over 945, they're the reciprocals of those numbers that we just looked at. So these values of gamma are going to tell us something about this table. Okay, now in the next video, we're going to start answering where do these formulas come from. Okay, why are the derivative of these formulas these ones? But we had to take care of some of this with the value of gamma, because actually the gamma function is going to help us to find the values of within this table here. In fact, before I even finish this video, let me kind of tell you the punchline in the next video. The value for v sub n of r, the volume of a ball of radius r when you're in n-dimensional space, is actually going to be 2 pi to the n over 2 times r to the n over n times gamma of n over 2. Okay, so notice this gamma function comes in. And we need to know the value of gamma of n over 2 if n is this nice whole number. So for example, if n is 6, we need to know, well, what's gamma of 3? Okay, well, we know that it's 2 factorial. Now, if n is 7, we need to know gamma of 7/2, but we found gamma of 7/2, right? That's what we just did, right? We found gamma of 7/2, right? It was 15 over 8 times the square root of pi. Okay, now you'll have a similar thing for the surface area formulas. And again, we'll go over this in the next video. I'm just trying to give you the punchline right now. S sub n of r is going to equal this. And notice again, there's a gamma function down in the bottom. Okay, so we'll get to that in the next video.